Hello friends, welcome to the session on multivibrators. In this session, we'll be discussing about monostable multivibrator. In this session, we will see what is the circuit diagram of monostable multivibrator, working of monostable multivibrator. We will also analyze the circuit in order to obtain expression for gate width of monostable multivibrator. Friends, as you know that you are viewing this session on my YouTube channel, Learn with Prakash Kanade, and do subscribe to the channel to see many videos on the subjects of electronics and computer science. So let us start the session, what we mean by monostable multivibrator. As we know that multivibrator is an electronic circuit which can has two states. These two states can be either stable state or quasi-stable state. Monostable multivibrator is a multivibrator which has only one stable state, and that is the reason it is being called as a monostable. So mono, it will stand for one. This multivibrator will have one stable state and one quasi-stable state. So in order to change the state of the monostable multivibrator, we need to apply one external trigger pulse. So when one external trigger pulse is applied to the monostable multivibrator, then at the output, one square wave is generated. So the other state of the monostable multivibrator is a quasi-stable state or temporary stable state. Monostable multivibrator is being also called as one-shot multivibrator because this circuit requires one trigger pulse in order to generate one square pulse, and therefore monostable multivibrator is being called as a one-shot multivibrator. Monostable multivibrator will produce a single output pulse for one input trigger pulse. So if you want to generate again one square pulse, then again you need to apply the trigger pulse to the input of the monostable multivibrator. Like a stable multivibrator, monostable multivibrator has also two states. The first state of the monostable multivibrator is one transistor on and other off. Say for example, Q1 on and Q2 off. Another state of the monostable multivibrator is Q1 off and Q2 on. So the circuit arrangements in the multivibrator circuits are such that both the transistors cannot be remain simultaneously on the on state, or both the transistors cannot remain simultaneously in the off state. So one transistor has to remain in on, then the other has to remain in off state. Now in monostable multivibrator, out of these two states, any state can be a stable state, and it will depend upon what kind of circuit is actually connected in the monostable multivibrator. Monostable multivibrator is a very useful electronic circuit because it is used to produce some time delays. This circuit is used in various applications such as in signal generator. This circuit is used in cathode ray oscilloscopes, and in televisions also the circuit of monostable multivibrator is used. Now let us go for the circuit diagram of monostable multivibrator. As shown in this diagram, this circuit consists of two active devices or two transistors Q1 and Q2. Emitter of both the transistor is being grounded. The collector of both the transistors is connected to the collector resistance RC1 or RC2, and the other terminal of the collector resistance is connected to the positive VCC. The collector of Q1 is connected to the base of Q2 through the capacitor C, while the collector of Q2 is connected to the base of Q1 through the resistance R1. The base of Q1 is connected to the negative power supply minus VBB through the resistance R2. And for the charging of the capacitor C, a resistance R is being provided in the circuit. So you will find that there is a slight change when you compare the circuit diagram of monostable multivibrator with a stable multivibrator. So as shown in the figure, the collector of Q1 is connected to the base of Q2 through the capacitor C. The collector of Q2 is connected to the base of Q1 through the resistance R1. Base of Q1 is connected to the negative power supply minus VBB through the resistance R2. Emitter of both the transistor is grounded. Resistance RC1 and resistance RC2, these are the collector resistances, and the other terminal of these two resistances is connected to the positive power supply. The output of the monostable multivibrator can be obtained at the collector of Q2. Now let us understand how the circuit of monostable multivibrator works. Suppose initially when we make the power supply switch on for the monostable multivibrator, then the circuit will go into the stable state. The stable state for this circuit is with Q1 off and Q2 on. The negative power supply is being connected to the base of Q1, and therefore we can say that the circuit will be stable with Q1 off and Q2 on. Now monostable multivibrator will remain in this state and for an indefinite interval of time. So if you want to change the state, then it is necessary that you apply the trigger pulse to the input of the monostable multivibrator. So either you can apply a positive trigger pulse to the base of Q1, or you can apply a negative trigger pulse to the base of Q2. So the transistor which is on, to the base of Q2, you can apply a negative trigger pulse, and to the base of Q1, the transistor which is off, you can apply a positive trigger pulse. Suppose the positive trigger pulse is being applied to the base of Q1. Now when the positive trigger pulse is applied to the base of Q1, the base potential of Q1 rises. When the base potential of Q1 rises, then you will find that the collector potential of Q1 goes on decreasing, because Q1 will go into the saturation state. And when Q1 goes into the saturation state, its collector current increases, the drop across RC1 increases, and therefore the collector potential will fall down to the saturation potential. This fall in the collector potential is immediately communicated through the capacitor C to the base of Q2, and therefore the transistor Q2 base potential will go down, and therefore transistor Q2 will go into the off state. When the transistor Q2 goes into the off state, its collector potential rises, and this rise in the collector potential is communicated through the resistance R1 to the base of Q1, and therefore we will go into the another state of the monostable multivibrator with Q1 on and Q2 off. Now you will find that the capacitor C will start charging through the resistance R and on transistor Q1. The voltage across the capacitor C will go on increasing exponentially. When this voltage rises, then the base potential of Q2 also rises. When this rise is sufficient, then again you will find that there will be change in the state of the monostable multivibrator. So when the base potential of Q2 rises sufficiently, then the transistor Q2 will go into the on state. Its collector potential will fall down, and therefore the base potential of Q1 also falls down, and Q1 will go into the cutoff state. That is, the monostable multivibrator has returned to its stable state without any external trigger pulse. So we will observe that the monostable multivibrator has returned to the stable state automatically. Now again, if you want to change the state of the monostable multivibrator, then again you need to apply the external trigger pulse. Now let us go for the analysis of the monostable multivibrator in order to obtain expression for the gate width. Initially, we will suppose that the transistor Q1 is off and Q2 is on. Therefore, the collector potential of Q1 is plus V. The base potential is less than the cut-in voltage V gamma. The base potential and collector potential of Q2 are the saturation potentials because Q2 is on. Now suppose the trigger pulse is applied at the time t is equal to 0. When the trigger pulse is applied, then the transistor Q1 will go into the on state and the transistor Q2 will go into the off state. Therefore, the collector potential of Q1 will fall down from V to Vc saturation. So this fall will be V minus Vc saturation, and the base potential of Q2 also falls down by the same amount. Therefore, VB2 at the time t is equal to 0, we call this voltage as the initial voltage Vi, which is Vb saturation minus V minus Vc saturation. Now the capacitor C will start charging through the on transistor Q1 and resistance R. The charging equation for the capacitor C can be given as Vt is equal to Vf plus Vi minus Vf into e raised to minus t upon 2, where Vf is the final voltage, which can be equal to the supply voltage V. Vi is the initial voltage, which is mentioned in the above expression, and Vt is the voltage across the capacitor at any time t. So when we substitute the value of Vf is equal to supply voltage V and Vi the initial voltage, then we can rewrite the equation Vt is equal to V plus Vb saturation plus Vc saturation minus twice V into e raised to minus t upon tau, where tau is the time constant equal to Rc. Now suppose at time t is equal to T1, the voltage across the capacitor becomes equal to V gamma cut-in voltage. And therefore we can rewrite the above equation V gamma minus V is equal to Vb saturation plus Vc saturation minus twice V into e raised to minus T1 upon tau. Therefore e raised to minus T1 upon tau is equal to V gamma minus V divided by Vb saturation plus Vc saturation minus twice V. The same equation can be rewritten as e raised to T1 upon tau is equal to Vb saturation plus Vc saturation minus twice V divided by V gamma minus V. So here we have interchanged the numerator and denominator. Now in this expression, we are interested in getting the expression for T1, and therefore we need to remove this E. In order to remove this V, we take the logarithm of both the sides, and therefore we can rewrite the above equation T1 upon tau is equal to log of Vb saturation plus Vc saturation minus twice V divided by V gamma minus V to the base E. The same equation can be rewritten as T1 is equal to tau into log of Vb saturation plus Vc saturation minus twice V divided by V gamma minus V to the base E. But we know that Vb saturation plus Vc saturation can be replaced by approximately equal to twice V gamma, and therefore T1 is equal to tau log of twice V gamma minus twice V divided by V gamma minus V to the base E. So this is just nothing but tau log of 2 to the base E, which is just nothing but 0.69 tau, which is equal to 0.69 Rc. So this is the expression for the gate width of the monostable multivibrator. That is, this is the time period of the quasi-stable state of the monostable multivibrator. And this time period will depend upon the values of resistance and capacitor used in this circuit. Now we can draw the waveforms of the monostable multivibrator. In these waveforms, we have shown the trigger pulse, which is a negative going trigger pulse, and the negative going trigger pulse should be applied to the base of Q2. So when the negative going trigger pulse is applied, we know that the state of the monostable multivibrator is changed, and now Q1 will go into the on state and Q2 will go into the off state, and therefore its potential will rise to almost supply potential. The voltage across the capacitor will go on increasing exponentially. When this voltage rises to the cut-in voltage, then again the state of the monostable multivibrator will be automatically changed, and now Q2 will go into the on state, and therefore its potential will fall down to the saturation potential, which is very close to the zero level. So from the waveform, one can easily observe that when one trigger pulse is applied to the monostable multivibrator, then we can generate one square pulse at the output. And this time period is the pulse width or gate width of the monostable multivibrator, and it will depend upon the values of R and C used in the circuit of the monostable multivibrator. So thank you friends for viewing the session. Hopefully you have understood the circuit diagram working and analysis of the monostable multivibrator. Thank you all for viewing the session.